Hi everyone, my name is Hendrik Bayer, and my talk today is about a paper I wrote with Michael Kaisers on online generalization in Monte Carlo tree search, in particular with multiple online value estimates. So let me start with a bit of motivation and an explanation of what we're trying to do here. Monte Carlo tree search, or MCTS, is the name for a family of sample-based search algorithms that have had amazing success over the last 15 years, for example in the field of general game playing, in the field of general video game playing, and of course in recent years as an integral part of several major reinforcement learning breakthroughs. MCTS is now a central pillar of both learning and planning in the AI community, which is why we'd like to improve its performance even further. Now, MCTS typically uses tree nodes to represent states or histories of the underlying domain, and these nodes collect online value estimates of the actions connecting them. However, there's no sharing of learned estimates between different nodes in vanilla MCTS, and therefore no generalization between similar states or actions. Most recent work on generalization has focused on offline generalization, for example by learning value estimates in advance, which can then be used in the tree during search. The neural networks usually used for this need to generalize over all states that any search is likely to ever visit in a given domain, which is why this approach needs such powerful function approximators and such huge amounts of data and time. In contrast to this, and orthogonal to this, we're interested in online generalization in search. The idea is to learn from similar states or actions while searching, which means that we can focus our estimates on the current episode and the actually visited states. And importantly, because there are often many ways to define similarity, and therefore many ways to generalize value estimates online, we're interested in making the best possible use of multiple online value estimators. Our main contribution is a method for combining value estimates into which any number of estimators or generalization strategies can be plugged in. And unlike most previous work on online generalization, we aim to apply this method uniformly in the tree as well as in the MCTS rollouts if they are used. In fact, we see the tree as just another estimator that can be seamlessly integrated into our method, which blurs the traditional distinction between being in the tree and outside the tree for MCTS. Now, before I get to how we combine value estimators, let me first explain which concrete estimators we've chosen for our experiments in several board game domains. We're calling them history abstractors. So let's assume we're in the middle of an MCTS search, at the red node representing the history that led from the root node down to the current state. And in order to proceed, we need the best possible value estimate for the red action, the red edge here. Where could we get this from? Vanilla MCTS gets its only estimate from the node we're currently in. This tree estimate does not generalize or abstract at all, but it has the advantage of being unbiased and converging to the true action value in the limit. On the other extreme, we can generalize across all nodes ever visited by pooling all of their value estimates for the action at hand. This basically assumes that all search histories are similar. It's a global abstractor. Other abstractors lie somewhere in the middle between these extremes. The OMA abstractor, for example, for opponent move abstraction, considers all histories similar that have the same past actions of the currently moving player. Here, for example, the move A0. It abstracts away all actions of other agents in the current history, leading to the two marked nodes having their estimates shared in our toy tree. Another abstractor we're using is based on the local context of the action in question. It considers all histories similar in which we can take an action with the same local environment, ignoring the rest of the state. Here shown with local 3x3 intersection contexts in the game of Go. And such similar actions then share their value estimates. All of these techniques have been individually proposed in the literature before. Here we're formalizing them all by framing them as history abstractors. And that allows me to get to our main contribution now. How to effectively guide MCTS with a collection of estimators such as these abstractors. That is, how multiple estimator Monte Carlo tree search works. So again, let's suppose we're in the selection phase of MCTS, in a node representing a history age of previously observed states and actions, and we now need to choose our next action among all legal actions. In vanilla MCTS, we typically choose the action that maximizes an expression similar to this one, an expression that consists of a value estimate Q hat for the action, so we can exploit our knowledge of which actions seem to be best so far, and an additional term called W here that expresses our uncertainty about this value estimate so that we can keep exploring and improving our estimates. In the popular MCTS variant UCT, for example, our value estimate would simply be the average of all returns that we've gotten so far when choosing action A after history age. And our uncertainty estimate would be this term based on how often we've chosen action A after age compared to how often we've seen age in total, and scaled with an exploration factor C that trades off exploration and exploitation. However, in this work, we're now assuming that more than one value estimate will be available for each action. Q hat then turns into a vector of estimates. For example, one estimate from the tree itself, one estimate from the local 3x3 abstractor, and one estimate from the global action value abstractor. What we want to choose now is the action that maximizes some combination of all available estimates, a convex combination in our case, again with an added uncertainty term for that combination. With a few simplifying assumptions, we can get this combined uncertainty from a weighted sum of the individual estimators' uncertainties, which leaves us with the main problem of our paper. What is the best weight vector lambda? Which estimator should we trust how much? So let's look at the problem of finding the best weighting, the best vector lambda. First of all, what's the optimal lambda? It's the lambda that minimizes the mean squared error of our combined estimator, compared to the actual unknown parameter we're trying to estimate, the Q value of the action at hand. Every action in the tree will have its own optimal lambda at every point in time, depending on which estimators have collected how much data about that action so far. So keep in mind that the following discussion is always relative to a specific action available in a specific tree node at a specific time step. Now it turns out that we can apply recent insights on optimally combining estimators, starting by rewriting this equation like this, where the matrix sigma is defined as the outer product of the errors of all individual estimators. If we knew exactly what the errors of all estimators are, we could then simply solve for the optimal estimator weighting like this, and we'd be done. However, we don't know the errors of all individual estimators a priori, so we need to approximate this matrix sigma. This is what sigma looks like for the example case of combining three estimators: the history-specific estimator from the MCTS tree itself, the 3x3 abstractor, and the global abstractor. On the main diagonal, we have the mean squared errors of the three estimators, consisting of variance and bias. And in the rest of the matrix, we have terms that depend on how these errors are related to each other. There are now many different approaches that one could take to simplify and approximate this matrix, and we're still exploring some of them. But just to give you a brief overview of what we did for the experiments in this paper. First, we assumed that all estimators are independent, which lets us set all non-diagonal entries to 0. Second, we know that the tree estimator is actually unbiased, so we could set its bias to 0 as well. And finally, we made the decision to treat the remaining biases as tunable parameters that are kept constant during search, and to estimate the variances of all estimators for each history action pair from the samples we've collected so far. You can check our paper for more details on how exactly we did this. And now that we've been through the high-level ideas behind ME-MCTS, let's see how well it works in practice. So far, we've tested ME-MCTS in 4 different board game domains: Breakthrough, Night Through, Othello, and Roll It. All experiments use 250 milliseconds per move in order to fairly take the overhead of computing and combining estimators into account. We looked at the three action value abstractors I've introduced before: the global abstractor, A global, the opponent move abstractor, AOMA, and the abstractor based on local contexts of 3x3 board squares, A3x3. And our experiments were divided into two sets. The first set used random rollouts for state evaluation in MCTS, and the second set used heuristic evaluation functions instead. Both approaches are quite popular in the literature, and ME-MCTS works with both. So let's start with the results for MCTS using rollouts. Before plugging multiple abstractors into ME-MCTS and combining them there, we tested them individually, that is, together with only the tree estimator of vanilla MCTS, to establish their performance as a baseline. Of course, the quality of an estimator combination technique strongly depends on the quality of the estimators that you put in. And we can see that individually, A global worked well in all 4 games, A3x3 in all games but Roll It, and AOMA in all games but Breakthrough. And then we go to the true test of ME-MCTS to the abstractor combinations. The dark gray bars here show in each game how well the best combination of any 2 abstractors played versus just using the best individual abstractor. And the light gray bars show the strength of combining all 3 abstractors in ME-MCTS versus only the best 2 for that domain. We can see that 2 abstractors were more effective than 1 in all test games but Roll It, and 3 abstractors were still better than 2 in Breakthrough and Othello, although there seem to be diminishing returns to adding additional estimators. Now for our second set of experiments using MCTS with evaluation functions instead of rollouts, we repeated the exercise. First, we tested all abstractors individually added to the tree to see if they're at all promising for an estimator combination. Here we found that all tested abstractors significantly improved vanilla MCTS in all games. And second, we tried all combinations of 2 or 3 abstractors with ME-MCTS. And again we found that 2 abstractors were stronger than 1 in 3 out of 4 domains. And 3 abstractors were still stronger than 2 in at least half of the tested games. These are quite promising results. And with a bit of additional testing, we found that the main limitation for ME-MCTS in our experiments was how simple the test domains were and how extremely fast both the random rollouts and the evaluation functions. In somewhat more complex domains, or with more expensive evaluations, such as neural networks, the overhead of ME-MCTS would be much less relevant, and we believe our method would be even more successful. So we've arrived at the conclusions and a little outlook on future work. Multiple estimator MCTS offers a promising method for combining multiple value estimators in Monte Carlo tree search. We've shown it to be effective in several test domains and in different MCTS variants. Here for the case of popular history abstractors from the MCTS literature, but ME-MCTS is not restricted to these. In future work, it would be interesting to explore different techniques for initializing and estimating the MSA matrix sigma. We'd love to do tests in more varied domains, especially in more lifelike settings that are probably less condensed than board games and therefore offer more opportunities for abstraction. It would be interesting to look at value estimators such as RAVE, which can be formulated as multi-valued abstractors in our framework. Abstraction could be combined with function approximation to kickstart the search from even fewer samples. And finally, there's the big challenge of learning optimal online generalization methods end to end. And that's the end of my talk. Thank you for watching, and goodbye.